Right, thanks very much. Let's have the first slide. Well, this paper is mainly about neutron scattering and the behavior of water on iron oxide. But in order to put that into context, I want to relate the neutron scattering technique to other techniques and some of the more traditional techniques shown on the left. That is, isotherm, surface area, porosity, and so forth, isosteric heats, calculation of adsorption energy, entropy, gas absorption chromatography, that's quite useful for investigating water absorption. And then the two, which I will refer to in more detail, because they relate to the neutron method, are infrared and dielectric. Now, as far as I'm concerned, this afternoon, the water molecule is famous for three reasons. It's polar, and that makes a big difference. It certainly allows one to use the dielectric method. Secondly, it can hydrogen bond, so we can use infrared. Thirdly, it's got hydrogen in it, and that's quite useful mostly for the inelastic neutron scattering because of the very high incoherent cross-section for neutrons. We also have XPS, that's almost a traditional method now, and a newer one, the laser-induced iron mass analysis, or LIMA. Those I refer to very briefly, because in fact other people did before us. You'll see that the neutron scattering is divided up into inelastic, which gives us information on molecular vibrations, quasi-elastic, which gives us the diffusive motions, and I'm not going to talk about that. John Ramsey later will talk on the quasi-elastic side, and then perhaps of some interest to the porosity people here, as I call them, the low Q, or small angle neutron scattering. So that's the broad scene. Next slide. It might be a good idea to start off very quickly with the Kislev work, in that sense, the difference between the isotherms of N-hexane and water on graphitized carbon black. Clearly the water molecule is a lot smaller than hexane. Hexane can lie flat on the surface. But the water molecule only gets going at very high coverage and does depend on any polar groups already present. Oh. Was that me or you? Now, to illustrate the complexity of the system, and remember we're going to talk in some detail about water on iron oxide, the sort of complexity we mean is that it's the other end of the scale from a non-polar gas absorbed on a non-ionic solid. Not that I suggest that such a system is simple, but that end of the spectrum differs from the other end, where you have an you have a polar molecule like water absorbed on an ionic solid. Here we've got examples of the simplification with sodium chloride. Iron oxide is, well, not as nice to use in that respect, but I want to just use this as an example. Sodium chloride is cubic, and enough data is available in terms of the electric field at the surface. This was done many years ago by Leonard Jones and Dent. And we also have summation terms for worked out also many years ago by W.J.C. Orr. Now, the terms we've used in this calculation are, in addition to the dispersion term with Müller, we have the electrostatic term, straight interaction with the electric field, and the water dipole. The induction term, which is half alpha F squared, alpha being the polarizability, F the field strength, and then we've got the worst of all, the repulsion term, which so frequently we approximate by R to B R to minus 12. Really, it's the best one can do because of the mathematics. Now, we've left out the quadrupole term, so before anyone thinks of jumping on me on that one, We haven't included that, but there are reasons why it wouldn't make a lot of difference. We know which way it would go. Now, A, B, and C, and D are the different sites on the surface. A is about the centre of a lattice square, that is consisting of two anions, two cations. B is the midpoint of an edge. C is above a cation, and D is above an anion. So you see here that the preferred site is in fact above the cation as far as our calculations are concerned. Now, that doesn't equal the isosteric heat, but it can be used to get a range of heats. And in fact, the experimental value we got for water on sodium chloride was about 44 kilojoules per mole, which comes quite nicely down on that. And we didn't refine the calculations until we got the right answer. So that's the sort of complexity that one is dealing with a water molecule adsorbed in a surface, in the environment of a surface electric field. Briefly, entropies. That's water on barium fluoride, comparison with the mobile model. We've used these occasionally. The best method, we think, is following the procedure published many years ago by Emmett and Hill and I forgot the other one now. Joyner. Where the method is essentially to integrate the Gibbs equation, and that means you've got to have quite good data down to low pressures. That tests out whether you've done the isotherm. They're fairly low pressure. Oh, that's with gas absorption chromatography. I brought in ethylene here. It should have been water, but it shows quite nicely in the Henry's law region. The trick or the method with gas absorption chromatography is to use the adsorbent as the stationary phase and elute the absorptive. And from the elution peaks, it's possible to get the isosteric heat of absorption. And we tried this with water and dichloroethane condenser walls, because that technique does not easily lend itself to condensable vapors. See what? Oh, that's the one dichloroethane. Nice isospheres. But with water, a little bit disappointing. 5 points on the line, 2 we ought to have rubbed off at the bottom there. So I'm not terribly happy about it. The actual value of the heat is what? It's 64. Now, this is on CuCl2. If it's above the cation, it would make sense in relation to water on sodium chloride, which we already have. Now, the dielectric method, this is a straight comparison. Sorry? They'll wave it at it as well. Well, yeah, that's what I thought. I was trying that earlier. We discussed this with the projectionist, and he thinks that might be... I'll try it anyway, but I want to keep it on for a moment, this one. All right? The dielectric method is important in relation to the two things. The fact that the water molecule is polar allows one to use that, and it relates very much to the neutron method, because now we're getting information perhaps on ice-like structures. And this is a variation of the dielectric relaxation time with coverage based on the krypton Newtonian surface area. The dielectric relaxation time, you will know, is related to the actual time for the dipole to come out of line with the electric field when the field is switched off. Now, ice at 298K is the line at the bottom. That was obtained by extrapolating the dielectric data of Orty and Cole. And the value is that which ice would have if it could exist at 298K. There's only one thing wrong with the dielectric method, and with all these methods, there's something wrong usually. The problem with the dielectric method is that if one uses a heterogeneous dielectric, there is no easy way you can subtract the solid and say, oh look, that's a property of the adsorbed water. Unfortunately, life is not so simple, and the complex effects of the combined electric fields mean you cannot do that easily. It's interesting information that ought to be taken into consideration with other evidence. What's next? Now that brings me directly onto neutron scattering. The comparison with infrared, well, you all know about infrared and pressed discs and diffuse reflectance and so forth. The one big disadvantage with infrared is basically you've got to press a disc that will stay with it. And it means a thin disc, so you've got to have a high specific surface area. Also, there are selection rules. Now, the neutron method has the advantage that you can use quite large samples. You don't have to press discs. Also, there are no selection rules. Otherwise, a lot of the information you get from inelastic neutron scattering is comparable with what you would get using infrared. This basically is an outline of possibilities. You'll see that frequently we refer to as the Q, which is the momentum transfer vector, and depending on the Q range which is available, and Q is the different wave vectors, K is 2 pi over lambda, happens to be convenient to use that form of vector language in this case. We've got the 4 possibilities: small angle or low Q. Low Q is perhaps a better, more accurate term. Elastic scattering, diffraction, structure which we won't concern ourselves with. Not much in relation to surfaces yet where that comes in, although I wouldn't exclude it. Quasi-elastic scattering, which gives diffusive motions, and one can measure, say, the variation of diffusion coefficient with coverage, or distance from the surface. And inelastic, which I will cover more, the inelastic and the small angle. And those are the different ranges. Now, with inelastic scattering, one basic apparatus which has been used, we have used, is the Beryllium filter spectrometer. And this is shown in the picture there. Essentially, I've got the pointer here. A neutron beam from the reactor is directed towards the center part B, which you see is a monochromator. That consists of an aluminium crystal with 110 planes lined vertically, and that just monochromates the beam by Bragg reflection. So, with a sample at D, it means a monochromatic beam of neutrons has been shown at it. Now, and this brings us to a very important point about neutron inelastic scattering and how it differs from X-ray scattering. And that is the neutron beam loses most of its energy in sending up or increasing the populations of higher states. The sample is cooled to a very low temperature to increase the population of the lower states. And that means that when the neutron beam hits it, these populations of higher states increase. The neutron loses a lot of energy, and, as I usually call it, the neutrons limp out, very, very tired now, into this beryllium filter detector, which happens to permit the passage of very weak or tired neutrons. The rest are Bragg scattered out of the beam into absorbers. So for a neutron to get through to the detector, it's got to be pretty damn tight. And by scanning a whole range of energy, you can cover the spectrum. That is the general principle. I'll show you the other one there. That's a schematic representation of the same thing. I'll try it that way. Yeah. The containers, aluminium, depending on the type of sample, that would be used in some cases, also used for, say, ice. And the measurement with ice has been a very important part of this work, because we want to compare. We're looking at ice-like structures, as you see. Another type of container. This is the beryllium filter spectrum of ice. It's quite complicated really, but all we're going to refer to are the central peak at about 80 MeVs, 80 MeV. That incident energy is also the energy transfer, actually, because of the particular method that I outlined. So that's the spectrum of ice. We have that central peak at 80 MeV and the shoulder at about 103. Now that central peak is thought to be dwellings, although certainly due to the librational modes about the two axes of highest moment of inertia. It's a libration, it's like a wobble, like a disco wobble. Think of the water molecule dancing in an electric field. Yes. Remember 80, the important point about the peak at 18 there. Because we'll keep coming back to that point when we look at other pictures. Here's the water molecule. There's a mistake I found to my annoyance in there. We left a minus sign from the moment of inertia. It's not 10 to the plus 37, so we're only actually 10 to the 74 out. A lot. So those are the sort of librations we're concerned with, and what the neutron technique will pick up. And we're slowly homing in on the iron oxide water system, and I'll refer now to work by McCafferty and Zettelmoyer some years ago, where the picture of the adsorbed layers is shown as we have here. And this will be relevant to what we refer to later. The beryllium filter spectra of water absorbed on, what is it? Can you see that? Yeah, magnetite. In Nigel Clarke's thesis, he uses all the words like magnetite, lipidocosite, I like that one, agonite or something, and then occasionally tells you what they are, like gamma Fe2O3, alpha Fe2O3, which you know is hematite, and so forth. So forgive me if occasionally I just say, well, this is lipidocosite. Okay. Now, this is the gradual appearance of the ice-like spectrum as the water coverage is increased. You'll notice that the peak is starting to form at around 80, ice-like. I remind you that with the ice spectrum we saw earlier, that peak was at 80 MeV. So here we've got the ice-like spectrum being formed. It's not quite the same as bulk ice as we might expect. The ice-like structure made with 1.3 or less than 2 monolayers is hardly likely to resemble the bulk, I don't think. It's more likely that it would be a distorting picture. So what we have to think about here is the fact that the ice spectrum is going to be distorted by the environment of the water molecules, differing, presumably, to that in bulk. All right, so let's try the next one. Oh, this is silica, water on silica. Now here's the difference. The central peak is shifted. That dotted line right down is the... Do you want me to use that? Shall I use that? So many gadgets. This dotted line is the ice peak, 80. Water on silica is shifted. This, we feel, is due to a reduced degree of hydrogen bonding. And one can do a fairly simple calculation to show that this fits with only 2 hydrogen bonds. So water on silica certainly looks very different from water on the other materials like the magnetite. Now we get on to another aspect of this. This is the beryllium filter spectrum of gamma Fe2O3. Gamma Fe2O3 is Magnemite. Nothing, this is outgassed at 200, nothing very no strong features, certainly nothing that would give rise to concern, interfering with an ice-like peak if that formed. Now what happens when we absorb water vapour? Now we have the water vapour absorbing in an ice-like structure. Very broad, but still the peak basically around 80. However, what happens when we leave that for a few days and do it again? So just notice for a moment, it's peaking around 80, fairly broad. Oh, surprise, surprise. After a few days, the 80 MeV peak has gone. There's 80. We've got peaks. These are just different subtractions of the background. But basically, the important point are these two peaks up here. And it turns out that those peaks resemble the beryllium filter spectrum of goethite, which is alpha FeOOH, right? B. Same. So, and this actually was confirmed by infrared. The initially ice-like structure absorbed on the surface of Magnemite has now changed to goethite. And goethite is formed in the outer layers. We estimate about 1.5 monolayers, basically. So the neutron technique can be quite useful in showing how changes occur on the surface. This is the using XPS. We were interested in the way, or whether small amounts of absorbed water remain as molecular absorbed water on the surface of some of these iron oxides, because that would reflect on how the ice-like picture would emerge at low coverage. And that's a wide survey scan, really, after that, that should be O1S, actually. This is the O1S peak deconvoluted using literature values for the clinical shifts relative to the O1S isolated atom. The three species being OH minus, O2 minus, and H2O. So this is the deconvolution program. This was done by Nigel Clark and Jay Watt at the University of Surrey with their deconvolution program. And here we've got the different peaks. That's the O2 minus, a lot of that, because there's supposed to be a lot of O2 minus there anyway. And that's the OH minus, and the H2O, they're quite small. Rather more was found in the case of halotite. No, we missed one. Another technique which can be used for this particular problem, that is finding whether small amounts of molecular absorbed water remain on the surface after extensive outgassing at fairly, well, ultra-high vacuum actually for a while. Both the XPS and the LIMA technique require ultra-high vacuum. LIMA basically is the firing of a laser pulse at a very, very small area of the surface. So one gets a power surge of 10 to the 12 watts per centimeter squared, and this causes a plasma to vaporize, and the resulting ions are then directed by a time-of-flight folded mass spectrometer to the detector, and you pick up the different ions that evolved. We were looking for the plasma phase cation H2O+, and there it is. So that confirms the XPS result. And there, as Nigel Clark commented, well, the water does hang about a bit when you try to get rid of it from the surface. It's quite strongly absorbed. So that's really part of the story of the iron oxide work. The other aspect of neutron scattering, which I wanted to cover, is small angle or low Q scattering. Here the technique is the neutron beam is from the reactor is refined by 4 high-speed choppers, revolving it up to 90 revs per second, I think. Either 90 or 900, I've forgotten. It's pretty fast. Then flight tube here, sample is contained in a 1 millimeter path length aerosol type glass container. And the scattered neutrons, forward scattered neutrons, are detected by a F3 Leti detector shown on the right. The neutron wavelength was about 6 angstroms, which was convenient for our purposes. Now what we're considering is the variation of the scattered intensity with Q, old friend Q. And Q relates to the angle. So we're looking for I against Q. Now, at high values of Q, the Porrod theory indicates there should be a variation of intensity, I, with Q to the minus 4. So the way to look at that is to have Porrod plots, which are plots of log I against log of Q, and we're looking for gradients of minus 4. The proportionality constant, I said that I is proportional to Q to the minus 4. The proportionality constant involves the surface area and enables one to get the surface area, provided it's a good Porrod plot, I think. Now, this is a typical example, log of I against log of Q. That's rather a nice one. That's our old friend Cableson. Now, what is important for good Porrod behavior is that the interface between the two phases is carefully, clearly defined. Now, two phases in a heterogeneous mix, in this case, the two phases are solid and then nothing or pores. Or one could have a collection of small particles in a matrix of air or vacuum. That is what the neutron small angle scattering method is picking up. It's differences in what is called the scattering length density between the two phases. And that difference, the interface between those two phases, ought to be quite well defined to give good Porrod behavior. Well, of course, Cableson is lots of little non-porous particles, so it's very good. Nothing fractal about it. What else have we got? What's that? Oh, alumina. Support for catalysts using oxychlorination and copper chloride type thing. That's quite nice, slope of 4. Well, it should be minus. There's a qualification there. Ought to be minus. We left a minus out. What's the next one? Oh, one can classify Porrod plots in relation to the sort of solid we're dealing with. And Ruth Williams did this with all sorts of different solids. So we know, usually by looking at the Porrod plot, what we've got. And an example, let's have a look and see what comes up here. We've got two of the worst examples possible for Porrod behavior. Activated charcoal and charcoal cloth. They just, well, they don't satisfy the Porrod law at all. They're so ill-defined. And that was the point I stressed. There must be a clearly defined interface between the two phases. And it looks as though there is in these two phases. That's another one. I think that's it. Oh yes, surface areas. I think I've got a couple of minutes. No, first of all, these are just the Porrod gradients for different substances. Quite a lot. Chromium, CR203 is quite nice. Oh, titanium is not very nice, up there. 3.3, that's the Fe2O3. They're not very good. Probably some porosity which is ill-defined. These are nice. Zinc oxide and MgO. And remember, the fact that it's -4 means it's a model system, not quite a model system, the interface must be very well defined. That's a high one. That's spherosorb, silica. Titanium quite good there again. So now let's look at the surface areas. One method here is from a variation on the theme. I won't really emphasize that. To look at general agreement in many cases. One of the points here is that all fairly low specific surface areas, and that means a better chance of being well-defined, a well-defined interface, and a better chance, therefore, of getting the right surface area. I apologise for the 1-point BET bit. Never did like 1-point BETs, but we had to in this particular case, and I won't go into all the details, but I regard this as the neutron method, checking on the 1-point BET rather than the other way around. All right? So there are some cases where it just doesn't look nice, but on the whole, it's not a bad picture. But and certainly with the fractal community, or the fractal concept of geometry, coming in many cases, I think that I would go along with that and say that perhaps the small angle scattering is best restricted to good toroid behavior. Thank you.
Do you think that what you described as a disappointing plot of the log of equilibrium pressure for a fixed amount of salt against reciprocal temperature for water on sodium chloride?
No, that was water on copper chloride, actually.
Your calculation showed...
Oh no, the calculation of sodium chloride, but the plot against reciprocal temperature, that was the isosphere, and that wasn't for water on sodium chloride.
What was it on?
Copper chloride.
Cupric chloride.
Cupric chloride.
It's a material which is soluble in water, and I wondered whether at the high temperature end, where the anomaly appeared, you were beginning to, the water was beginning to penetrate. In other words, the surface was getting heavily perturbed.
Yes, that's a good point. I was perhaps more wondering whether it was the difficulty of the technique that was showing up, because basically that technique requires an injection of the gas. The chromatographers here, is that what they call them? They might know more about this, but it's tricky to inject a liquid and to get it to vaporize in the right way so that you get the conditions of the dosage right, because the dosage has to be varied and must keep in the same place. So perhaps I was more concerned with that. But I think Professor Barrow gives me great heart by saying that and indicates that it could be for reasons beyond our control. Thank you.
That's a comment and question regarding your last remarks about application of small angle neutron scattering to activated charcoals. We looked at the application of small angle X-ray scattering to activated charcoals a few years ago and found similar poor behavior to the Pauli law. And our view was to, it adds a little bit to what you said, I think. It's not only that the interface between the solid and the pore has to be sharp, it's also an assumption that the electron density within the solid is uniform. If there are
the
electron density of the solid, then that too will contribute to scattering. And in a carbon, you have a highly defective internal structure in the solid, and you also have petroelements contribute to the poor vacuums to the boron law. You take activated charcoal to heat them up to over 2,000, get rid of the heteroelements and improve the structure, and then you get adherence to the boron law. The other point I wanted to ask your comment on, I have a note here regarding the hydration of Magnemite, gamma Fe2O3. Yes. Your evidence suggested, you said, that there was 1.5 monolayers of goethite formed on the surface.
So I meant really the amount of goethite corresponding to 1.5 monolayers of water reacting.
Okay. You've got the perhaps
But I mean, we don't really know.
Yeah, it seems, did it seem physically realistic to have, how could you be sure that if you're dealing with that small amount of material that is in fact goethite?
Well, we can be sure it's goethite because of we did the spectra of all the others, and it's almost identical to the spectra of bulk goethite. The second slide I showed was bulk goethite.
Is there sufficient goethite formed to
yes.
get out form
Yes, because that Magnemite, the outgas spectrum was fairly flat, so anything would point up beyond it. So.
This question of the goethite formation, I was going to ask about that later. This is not unusual as far as I can see, because one picks up this oxide hydroxide structural formation in other cases.
This is what led us on to that.
Yeah, that's
yes.
right. I think that what it does is to involve interaction with the cation. So you've got dissociative chemissorption taking place as a result of strong H2O cation interaction.
Yes, that's right. Yes.
I think that's the part. Now, there must be sort of reasonably well-defined conditions, presumably, to allow that to take place. I don't know whether you've studied that. I mean, what happens, for example, if you only take a fraction of your water monolayer? Presumably, you wouldn't pick it up under those conditions.
Well, we didn't try that. I don't think one would.
Yeah, you'd have to get up to pretty high coverage.
I think so, yes.
Right.
We've had no evidence of anything like this with any of the others. Yeah. It was just that almost by chance it was checked out by 10 days later.
It fits in, of course, with some of Wick Roberts' work.
I know, yes. Yeah.
Yes, so it's very interesting.
Yeah.
Thank you very much.
Thank you.